All right, it's 3:05, so let's get started. Final quiz out tomorrow, Saturday. So on Blackboard, I have a little entry that shows you the number of points you got with the lowest 3 quiz scores drop. That's not actually how we'll compute quizzes, but it just gives you a rough idea. The real way is 6 through 10, consider that full credit. 1 through 5, full credit. 0, no credit. And then we'll drop the lowest of those 3. Final exam review Thursday. I'm doing it in class. Okay. Any questions before we start?
What's the real way again?
What was there?
What was like the cutoffs again?
Cutoffs for
6 to 10 is full credit.
Oh, yeah, for quizzes. 6 through 10, we'll consider that full credit. 1 through 5, we'll consider that half credit. Per quiz, yeah. And then we'll drop the lowest 3 of those. Yeah. They're almost worth nothing, so it's not even that big of an issue, but yeah. Any other questions? I know you were behind one.
Yeah, that was the same.
Okay. Any other questions then?
Thanks.
Okay, so what did we talk about last week? Yeah, undecidable languages. Yep. So undecided. All right, undecidability. So, what languages did we show were undecidable?
ATM.
ATM was one of them. So ATM, that was the set of all machine and input pairs. So there is a TM, and this string is in the language map. And we showed that that was undecidable because if we had a decider for it, then we can make a machine that could disagree with its own self, right? And that can possibly exist, so therefore that's undecidable. Well, let's see. What else did we show was undecidable? What's another one we showed was undecidable? Yeah, ETM, yeah. So we showed that ETM, which is what was just said, the language of all Turing machines, descriptions, and that have empty language. And we showed that was undecidable. How? We'll get to that in a second. But you can. But what was the way we did it?
Based on that you need a decider for ATM first, and then based on that option, then you can decide whether or not
The other way, yeah. But the idea is right, yeah. So if I did have a way to decide ETM, then we found that if you did, then you will have a decider for ATM. But we know one cannot possibly exist for ATM, so there can't be one for ATM. And the way we did that was we made a machine that simulated M on W and had empty language if M exists. So there are many ways you can approach it, but all right, well, we proved those 2 undecidable. What else did we do? Well, we did multi-M, so similar flavor. But what else did we do to get a whole bunch more? Rice. Yeah. So what did Rice's theorem talk about? Yeah, so something about all non-trivial properties, but properties of what? The languages, yeah. So of the language, but language of Turing machines, obviously. But what about Turing machines? It's Turing machine descriptions, right? Because we can't have a language of Turing machines, but we can have one of Turing machine descriptions. So it's the language of Turing machine descriptions. And what did Rice's theorem say based off this? It's undecidable. Oh, all of these are undecidable. So let's back up for a second. When we used ETM to solve ATM, what did we call that? Using ETM supposed decider to solve ATM, what did we call that? A reduction, yeah. So we showed that ATM reduces to ETM. Okay? So notationally, this means if I can solve ETM here, then I can solve ATM. Okay? But what did Rice's theorem use on the back end? Or how did we prove that? I think it's via a reduction from what? ATM. So via a reduction from ATM. And the idea was that we're going to make a machine as the first step. The behavior of the machine will be some machines that has the property if M accepts W, and it'll behave like another machine that doesn't have the property if M does not accept W. So if I had a decider for the property, I can decide ATM. So let's see. Can I use Rice's theorem to prove ETM undecidable? Well, we gotta check. Is it entirely full of Turing machine descriptions? Does the ETM only have Turing machine descriptions? Yeah, it only has Turing machine descriptions right there. All right, so that's a good check. Ignore non-trivial for a second. Is it a property of the language of Turing machine descriptions? So if I have two Turing machines with the same language, could it ever be the case here that one of them has the property and the other one doesn't? No, because if they had the same language, either they're both empty or they're both non-empty, because they're the same. So this is a property of the language of Turing machines. Is it a non-trivial one? So can I find a Turing machine that has the property and another one that doesn't? Yeah, easily. If I can, one machine that rejects everything, that'll be in here. One machine that accepts everything, that's not in there. So therefore, it's a non-trivial property of the language of Turing machine descriptions. Therefore, ETM is undecidable via Rice's theorem. So that's easy. Can I use it to prove ATM undecidable? Well, ignore the fact that essentially that would mean you're doing a reduction from ATM to ATM, but ignore that. Can I use Rice's theorem for ATM? Well, let's check. Is it full of Turing machine descriptions? Only Turing machine descriptions. Sure. Is that a Turing machine description? No, it has an input with it. So I can't apply Rice's theorem because it is not entirely of Turing machine descriptions only. Okay. Suppose back in ETM where we could apply it, I changed it to add on this. And M has at least 5 states. Can I use Rice's theorem for this modified ETM? Well, let's check. Is it full of Turing machine descriptions? Yes, that's good. Is it a property of the language? Could it be the case if I have two machines with the same language? One has the property and the other one doesn't. as an example, I could have a machine with 6 states and another one with 4 states with both empty language. One would be in there, one wouldn't be, and they have the same language. So I can't use Rice's theorem to prove this undecidable. It is undecidable, but I can't use Rice's theorem for it. So I can't use Rice's theorem everywhere, but I can use it a lot of places. Any questions about these? No? Yeah.
Did anybody know when you can use Rice's theorem, or was it one of those things where you just kind of have to know?
It's very easy to tell, and we'll do both ways in these. But any other questions? Yeah. All right. So let's do this problem infinite TM. And I claim it's undecidable. So let's do the easy one first. So let's do Rice's theorem approach. We'll do a direct reduction after, but let's use Rice's theorem first. Well, let's see. Is it a language entirely consisting of Turing machine descriptions? Yeah, I better hope so. Yeah, it just has Turing machine descriptions, so that's good. Is it a property of the language of Turing machine descriptions? So if I have 2 machines, M1 and M2, with the same language, could it be the case that one of them is in infinite TM and the other one isn't? Sure. Well, if they have the same language, it's either they're both infinite or they're both not infinite because it's the same language. So then that must mean either both are infinite or both are finite. And then that means that M1 and M2, both M1 and M2's descriptions are in infinite TM, I'm abbreviating, or they're both not. Right? It can only be the case that they're both in there or they're both not. So it is a property of the language, so that's great. Is it a non-trivial property? Well, let's see. Can I make a machine that has infinite language and another one that has finite language? Yes, certainly, yes. So let M1 be a TM that accepts everything. Then, therefore, its language is infinite. So M1's in infinite TM. Then let's let M2 that rejects everything. Then therefore I know M2 is not in infinite TM. Okay. So I know of a Turing machine that is in there, one that isn't. Oh, that's a non-trivial property. Okay? What can I say now? It's undecidable. How do you know? By Rice's theorem. If I don't put those 3 words, this doesn't make a whole lot of sense. But if I say by Rice's theorem, then I know I'm applying Rice's theorem, and then therefore I can claim it's undecidable. So by Rice's theorem, so those are the most important 3 words of this whole thing. This language, infinite TM, is undecidable. Okay. All right. Any questions about that? All right. right, well, let's do an actual reduction. So from some undecidable language that we already know, I want to, assuming infinite TM is decidable, I want to make a decider for this known undecidable problem. So any choice as to what undecidable problem to reduce from? We have several choices. What does Rice's theorem use on the back end? I think it uses a reduction from ATM. So maybe we can reduce from ATM. It'll turn out we can reduce from anything, but let's reduce from ATM. So ATM, let's reduce it to infinite. So I gotta assume a decider for infinite TM. Then using that, I'm gonna make a decider for ATM. So suppose D decides infinite TM. Then I'm gonna use it to my advantage. Okay? So if I'm gonna make a machine for ATM, what should I take as input? What should I take for ATM? The Turing machine and a string. All right. So on input MW, where M is ATM and W a string. I can't say W is in the language of M because I can't obviously check that. So let's see. Well, D is a decider for infinite TM. So what does D take as input? I think just a single machine, right? Because that's how the language is defined. So if I feed M to this decider, supposed decider D, will that tell me anything about whether M accepts W? No, because even if it was infinite, that doesn't tell me whether it accepts W or not. And even if it was finite, it wouldn't tell me that either. So I can't feed M directly to D. So let's make a machine that gets us the behavior that we want. So let's construct a machine M prime. And this is going to take an arbitrary input. Okay? Well, let's see. I want this machine M prime to be eventually feeded to D. Okay? So D, when we feed it to that, will say yes or no, it has infinite language. So I want M prime to have infinite language if and only if M accepts W. Okay? If I can do that, then the decider for D can tell me something about ATM. Okay? Which is what I wanted. So let's see. What's your favorite finite language? Any choice? It actually won't matter. Finite language. Oh, it's the 14th week. 15th, I think. But finite language. Empty. All right. What's your favorite infinite language?
Sigma star.
Sigma star. That's a perfectly good one. It actually doesn't matter that it was empty set or sigma star. All I needed was that I need one to be finite and I need one to be. Well, let's see. What could I do? Well, what I could do is, by default, I'll be the finite language. language. I'll have M prime be a finite language by default, no matter what. But if M accepts W, I'll make it an infinite language. Okay? Well, we picked empty set. It didn't matter, but if we picked empty set, does M prime right now have language empty set? Sure. Does it accept anything? Does it? Is the word accept in M prime's description? No, I said at this point. So it has language empty set right now, so we're already at the language we want to default at. So now I want to feed M, run M on W, and I want it to become sigma star if M accepts W. Okay? So I'm going to run M on W. If M accepts W, then we are going to accept X. Okay? Well, let's see. What does this mean? Once I start making this machine M prime, is the fact of whether M will halt on W or not fixed? Sure. Once I have my specific machine M and specific input W, is it going to either run forever or stop with certainty? Yeah, one of those two is going to happen. So, let's see. Well, it may be the case that M accepts S or not. M accepts W or not. If it accepts W, is it always going to accept W in this machine throughout the course of this running this machine? Yes, because M, if it accepts W, that's a fixed known thing to be true. So at this point, M will always accept W. So will I always accept X in that case? So if M accepts W, I'll accept every string X. So what language would M prime be? The infinite sigma star. If M does not accept X, so that's a fact, M does not accept X, what will the language of M prime be? It'll be empty set. Fine, but yeah, empty set. So I'm gonna, so another thing. You say, Ryan, that is wrong, you silly fool. Run M on W, that takes an infinite amount of time possibly, right? There's something wrong here. I don't want to make sure I'm cheating here. Is there something wrong here? Am I running M prime? No. I'm just telling you how to make the machine. And then I'm going to feed it to a supposed decider that will always stop. All right? So I'm never running M prime myself. I'm feeding it to D, letting D do its own thing. It has a contract that says it'll always stop. And then therefore, I'm going to wait until it gives me the result, which I know it will because I know it is a decider. So run D on M prime. If D accepts M prime, we get something. Then if D rejects M prime, then we get something else. Well, let's see. If D accepts M prime, what does that tell me about M prime? It has infinite language, because that's what D does. Well, if M prime has infinite language, what was the only way we could have gotten infinite language before? If we accepted X here. But the only way we could have accepted X here is if M accepts W. So for my supposed decider for ATM, what should I say now? I just determined M accepts W, so what should I say? ATM. All right, that's what we would do if D accepts M prime. If D rejects M prime, for similar reasoning, we know now M prime's language is finite. So if we come back here, the only way we could have had finite language is if we never made it to this accept step. But the only way we couldn't have made it here is M did not accept W. So what should I say to my decider for ATM? Reject. Yep. And then now we just made a decider for ATM, but that can't exist. So therefore, ITM, infinite TM is undecided. Because if it were, then we would make this decider for ATM. Okay. Any questions about those two approaches? We actually kind of did what Rice's theorem does on the back end. We make this machine that has a certain behavior if M accepts W and has other behavior if it doesn't accept W, depending on what the language is. Okay. Any questions about that? Okay, so let's talk about this problem. So it's not that different, except now we want to check whether the empty string is in the language or not. And this is undecidable. Well, can I apply Rice's theorem? Well, is it a language only consisting of Turing machine descriptions? Yep, so that's an easy check. Is it a property of the language of Turing machine descriptions? So, if we have L of N1 equals L of N2, could it be the case that one of them is in ESTM and the other one isn't? I don't think so, because if they're the same, then either the empty string belongs to both or it belongs to neither. So therefore, they're both in or both out. So, same conclusion. The same conclusion we got here. Well, let's see. Can I show that this is a non-trivial property? Can I find a machine that does have the empty string in it and another one that doesn't? Yeah. Examples? How about those two? Same examples. Yep. And then therefore, by Rice's theorem, ESTM is undecidable. So it's actually interesting. The conclusion is almost as long as the proof, but anyway, you can apply Rice's theorem here because the language of Turing machine descriptions only, so that's a check, is a property of the language, which we checked, and it's a non-trivial property. And then therefore by Rice's theorem is undecidable. Any questions about that?
Can you repeat the last part, just the last thing?
Yeah.
Just
The checks?
what are the things we need
Yeah.
to use it?
Yeah, so it's all here. But the idea is, does it only have Turing machine descriptions? Yes, that's a check. Do they have, if you have two machines with the same language, could it ever be the case that one of them that has the property and the another one doesn't? And we determined here, no, that's never the case because if they have the same language, they're both in or both out. So that's property of the language. And then we gotta check, is it a non-trivial property? Could I find a machine that has the property, that has empty string in its language, and could I find another one that doesn't have empty string? Okay. Any questions about that? So I bored the last two recitations with doing a direct reduction, but it turns out to be almost identical to this one. So why is it identical? Because I'm going to reduce from ATM, but I could do another one. But if I did it from ATM, then this part would still be the same. Then I got to make a machine M prime, because if I feed M to this supposed decider D for ESTM, then that doesn't tell me whether or not it accepts W, right? It doesn't tell me anything. So what I do here is I make this machine M prime. Well, what's a nice language that has the empty string in it? Single star, easy. What's another one that doesn't have empty string? How about the empty set? Same examples as before. So I'll start off by accepting everything in the empty set. There's nothing. Then, if M accepts W, I'll accept everything. And so we'll get exactly the same conclusions as before. Okay? Any questions about that problem, though? Because I want to do one that's not on the handout that was brought up last section. That I think is even more interesting, because it uses a different reduction. All right. So it's called sub-TM, and it's all pairs of Turing machines. So this is not on the handout, but I have two machines, M1 and M2. And the first one's language is a subset of the other. So that might be something you want to check. If you have a specification and you have a system, you want to check, does the system satisfy the specification? And this is undecidable, unfortunately. Well, let's see. Could I use Rice's theorem here? Well, let's do our checks. Does it consist of Turing machine descriptions? Yes, be careful. Single Turing machine descriptions? No. It's consisting of pairs of Turing machines. Therefore, I can't apply Rice's theorem. It only applies to languages with single Turing machine descriptions, like ESTM, Infinite, ETM, all those. Okay? So this one has two, I can't use it. Well, let's see. How am I going to do, I have to do a reduction, because I can't use Rice's theorem. So what would be a nice language that I could use? Well, I could do ATM, but I don't want to do ATM. So, what language would be nice here? I could do ETM, but what's one that's even closer to this one? What was another one we proved undecidable that's very close in name to ETM? How about EQ ETM? We proved that one undecidable as well. So, let's reduce EQTM to sub-TM. So now I gotta suppose I have a decider for sub-TM, and if I do, then I can make a decider for EQ. Okay. So let's suppose D again decides sub-TM. Well, if I'm making a decider or whatever for EQTM, what should I have it take as input? Yeah, it takes two machines, yeah. So on input M1, M2, where M1, M2 are TMs. Well, I gotta use this decider D to help me here. How can I use the decider D to help? Well, if M1 and M2's language are the same, what do I know about containment? Well, they're the same language, but in terms of containment or subsets.
Subsets of each other.
They're subsets of each other. Oh, could I run the decider twice? Yeah, certainly, because it's a decider, supposedly. Good question? Okay. So, run D on, well, I gotta do one direction. I wanna check that M1 is a subset of M2, and I wanna check if M2's language is a subset of M1's language. So then run D on M2, M1. Okay. Well, in order for me to say yes, they are equal, what should both of these say? Except, yeah. So if both, I guess, simulations or runs accept, then we will accept. Otherwise, they can't be equal, so I should say reject. Okay. So it's not like this reduction that we've already seen where we're reducing from ATM and we gotta make this machine in there and we only run the decider once. Here we can run the supposed decider many times. Okay? As long as it's a finite number, I can run the decider as many times as I like. Okay? And it's nice here because I only have to run it twice. And I just flip the order, and if both answers say yes, then I know they're equal. Any questions about that one? All right, so let's do this other one. How many of you heard of CSE355? So if you so the grad version of this class, this next problem was actually a homework problem when I took it, believe it or not. So we'll actually solve a graduate level problem here, which is nice. So this is number 3. So this function L of M is, all it is just keeping track of all the strings in the Turing machine's language. Okay? So for example, if M accepts every string, then it'll contain a string of every single length, and then therefore L of M in that case would be 1 star. Similarly, if M does not accept anything, then L of M would not contain anything. So it'd be the opposite, and therefore it is regular. So I want to ask the question, are the lengths of the given Turing machine regular? So M is a TM, and L of M, this little L of M, is regular. Okay. Can I apply Rice's theorem to this problem? Let's check again. Does it consist entirely of single Turing machine descriptions? Yep, that's easy to check. Is it a property of the language of Turing machine descriptions? So let's check. If L of M1 equals L of M2, could it be the case that one of them is in reglen-TM and the other one isn't? No, and the reason is, if they have the same language, then they'll have the same L of the machine. And if they have the same L of the machine, both of them are regular or both of them are not regular. So, because they have the same language, L of this little L of M1 must be little L of M2. And then it's pretty easy to see that either both of these little L's are regular or both not regular. Okay, so that's easy. Is it a non-trivial property? So could I find, well, let's do an easy one. Could I find a machine where the length set, I call it, length set, is regular? Yeah, what's an example? How about one that accepts everything? Therefore, the length language is 1 star, and that's obviously regular. So, M1 accepts everything. Therefore, M1 is in regular. But now, I need a machine that has non-regular lengths. So we have to think a little harder about this one. What is a language that we saw that has non-regular lengths? So there are many examples you can come up with, but an easy one is to have a unary language. So it only has one character, and so therefore the lengths of those are just the strings themselves. So is there a unary non-regular language we've seen? Yeah, prime number. Exactly. So M2 with L of M2 being prime number. And we've seen this twice in recitations. We showed it was not regular, and then we eventually showed it's not context free. But it is decidable because we can check whether something's a prime number or not in a finite amount of time easily. So therefore, this length is just the language itself, just substituted 0 for 1. And then therefore, its L of M is not regular, and therefore it's not as regular. So M2 is not in regular. Okay? And that shows us a non-trivial property, so therefore, by Rice's theorem, Reichland is undecidable. Okay? So it's just an application of Rice's theorem. I want to do a direct reduction though, because it'll get us to think a little bit about it, what we need to do. So let's reduce ATM to this problem. We could choose anything, but ATM is easy. So suppose D decides right length. Then we gotta make a decider for ATM. So exactly the same. Let's see. If I feed M into D, will that tell me anything about whether M accepts W or not? Not necessarily, because it could be that W has prime length. And if M accepts only the things of prime length, it will have non-regular language, non-regular lengths, but it will still have accepted W. So it doesn't really tell me anything. So again, we gotta make a machine. So let's again construct M prime with input X. So we have to think a little harder about this one. So let's see. What do we need to do? We need to accept a non-regular length language first before we even do anything. Because if, it's now erased I guess, but if M does not accept W, I won't accept anything else afterward. So I need to, at the beginning, accept things that I want to get to a non-regular language. Okay? So what's a non-regular language that has the non-regular length language we could do? How about that? Right? So let's see. Maybe what we can do is, if x's length is prime, which we could check, let's accept it immediately. So whether or not m accepts w, I'll have primes, lengths, strings. If m accepts w, accept everything else. Well, if I accept everything at that point, what will the language of m prime be? Sigma star. Is sigma star's length regular? Yeah, it's just one star, which is regular. So let's do that. If the length of x is prime, accept x immediately. But if m accepts w, accept everything else. If it wasn't accepted up here, it will be accepted here. If m accepts w. So run m on w. If m accepts w, we'll accept x. Well, what is the language of m prime? Well, it will always have the prime length string, always. But if m accepts w, then we'll get everything else. And then therefore, the lengths language would be one star, which is regular. But if m does not accept w, what is the language of m prime? Can it ever accept anything of non-prime length? No. Right? If m does not accept w, I'll never come down here and accept anything else. So the only things I could accept in that case are a prime length. But is the length of prime strings regular? No, because we've seen that that's not regular. So now we know what happens. So if I need to run this supposed decider D on m prime. If D accepts, and if D rejects. Well, if D accepts, what does that mean? That means that m prime's length is regular. But what does that mean? What had to happen here?
They accepted W.
Right, m accepted w. So for my decider for ATM, I need to say, not reject, accept, because if it has regular lengths, then that must have meant m accepted w. But I'm trying to decide whether m accepts w. So I should say accept. Okay? Well, if D rejects, what does that mean? That means that m prime's language is, the lengths of the strings is not regular. Well, what does that mean? Could I have ever come down here and accept x down here? No. So that must have meant m could not have accepted w. Because if it did, I would have come down here. So therefore, for my decider for ATM, I should say reject. And that's how it goes. Any questions about those examples?
Basically, we're using a strategy that we built a decider for regular length TM, then that can be reduced to ATM. So if we have a decider
I'll
for that,
go back.
we have a decider for ATM. But obviously, we can't do that, but therefore, ATM.
Exactly. Any other last minute questions? Yeah.
And so don't take it, so you don't.
Yeah, I don't care if I don't accept. Yeah, because I'll never get to the accepts part yet. Any other questions? Thank you for coming to my recitations.
Is this the last recitation?
Yeah.